All right, in this podcast, we're going to talk about how to actually make a buffer. So, lots of times, because of how useful buffers are at resisting changes in pH, it's something that is commonly done in industry, medicine, etc. All right, so there's two things you need to keep in mind when you got to build a buffer. Number one, you got to get the pH correct. So the pH of the buffer is primarily determined by the pKa of the weak acid and the conjugate pair. We know that when the acid and the conjugate base are equivalent, that the pH is equal to the pKa. So we want to choose a conjugate acid-base pair that has a pKa that is close to the pH we desire. We can adjust the concentrations or the ratios of our acid and our conjugate base from there to tweak the pH a little bit. But it's really, you can't really tweak it more than about 1 pH unit from the pKa. The other thing you have to keep in mind when building a buffer is buffer capacity. So if you know the amount of something, acid or base, that your buffer is going to be subjected to, that can help you in order to make sure that you have a buffer that has a high enough buffer capacity to be able to neutralize that added acid or base without having a big change in the pH. All right, so again, choosing the pair, all based on the pKa of your weak acid or pKb of your weak base. And again, make sure that your pKa, pKb value is not more than 1 pH unit away from the desired pH of your buffer, or it's just not going to work. Okie dokie, so here we're going to look at this data table and decide if each solution is an appropriate buffer for the pH range desired. Okay, so we desire a pH of 1.5 on our buffer. This is our pKa. This is the difference. So no, this is not going to work out. All right. This one we desire a pH of 2.4 and the pKa is 3.14. So that's a 0.74 difference. So yes, this will work. This is good. Okay, the next one we want 5.3, 3.14, way too far away. So definitely not going to work. Okay, the next one we want 8. pKa or pKb is 9.26. Too far away, so not going to work. And then 9.5 and 9.26, that is going to work. All right, so suppose you're required to create a 0.5 liter buffered solution where the acid and conjugate base have similar concentrations. Using the info below, select the weak acid and conjugate base pair that would be used to create the buffered solution with a pH of 4.8. All right, so we're given two acids down here, and we're given their Kas. So the first thing you need to do is you need to get their pKas. All right, so if we negative log their Kas, we get a pKa of 3.18 and 4.74. All right, we want our buffer to be 4.8, so this is the acid that we're going to choose, and then of course we would need its conjugate base, which is going to be that. So we need this and this in around equivalent concentrations for this buffer. All right, now in this example, we want to create a 1.35 liter phosphate buffer that has a pH of 7.29. So we need to select which pair below is going to be the best thing for us. So if I want a 7.29, that is closest to the pKa2. So I'm going to pull these species. So I want to use this and this as my weak acid conjugate base pair in order to create that buffer of that pH. All right, now as you've seen, it's very common that the exact pH that we want our buffer to be is not going to be equivalent exactly to our pKa or pKb. So we can use Henderson-Hasselbalch to adjust our pH just a little bit by adjusting the ratio of weak acid and conjugate base that we have. But remember, we can only adjust it by plus or minus 1 pH unit from our pKa. All right, so if I want to change the pH of my weak acid buffer, then what I want to do is I want to make sure that first off I understand what's in my buffer solution. So to make a buffer with this weak acid, HF, I want to add a salt of its conjugate base, so KF. So these two guys right here are going to be my pair. And if I need to adjust my pH with that, I have to understand what I'm looking at. So if I want to lower my pH from where my pKa is, I want to add more weak acid than I have conjugate base. If I want to raise my pH, then I need more of the conjugate base than I have of the weak acid. Conversely, if I have a weak base buffer, I have my weak base and its conjugate acid, salt. So if I want to raise my pH, this one's a little bit, you have to think of it backwards when you're changing the whole situation, you're flipping it. So if I want to raise my pH in a weak base buffer, then I've got to add more weak base than I have conjugate acid. If I want to lower my pH, then I need more of my conjugate acid than I have of my weak base. All right, so let's look at this example. So how many moles of NaOCl must be added to a 650 milliliter solution of 0.5 molar HOCl to create a buffered solution with a pH of 7.5? And then it gives us our Ka value of our HOCl. We also are told to assume that the volume does not change, which makes our life a whole lot simpler in this situation. All right, so the first thing I want to do is I need to get the pKa of this acid. All right, so if I negative log my Ka, my pKa is 7.46. Okay, so I'm going to get my equation out here, Henderson-Hasselbalch. And, oops, put the wrong one on top, didn't I? Alrighty. So I got my conjugate base and weak acid. All right, I want my pH to be 7.5. My pKa is 7.46. And then I've still got my log of my acid over my base over here. I mean, my base over my acid. All right, so I need to basically figure out what I need that ratio to be. So I'm going to subtract, get everything on simplified. So I got 0.04 is equal to the log of my conjugate base over my acid. All right, now this is a log base 10, so to get rid of it, raise the other side to 10. So this is going to give me my ratio. Okay, all right, and I've got, okay, so 10 to the 0.04 gives me, all right, so that's 1.09. So my ratio is equivalent to, well, actually, if you round, it's 1.1. So let me correct that. Okay, so I got 1.1 is equal to my ratio of my conjugate base over my acid. Now, I'm told my acid concentration is 0.5. So if I plug that in, I got 1.1 is equal to this over 0.5, and then cross multiply. All right, so when we cross multiply, we get 0.55. So that's the concentration I need of my conjugate base. Okay, now I know that my solution is going to be 650 mils, which is 0.65, and then my moles is on top, so I solve for my moles, and I get that I need 0.3575 moles of the NaOCl. All right, now looking at this example, we want a pH with we want a buffer with a pH of 3.5. We need to find out if HF or Na is going to be, HF-Na pair or the H2CO3 NaHCO3 pair is going to be better. We're giving the Kas for both of these acids. So if you go ahead and get the pKa's of these acids, so for HF, the pKa ends up being 3.14, and for the H2CO3, the pKa ends up being 6.37. Okay, so if we want a pH of 3.5, we definitely want to go with the HF-NaF conjugate pair for our buffer. Okay, the next question wants to know what ratio we want for our buffer so that our solution is going to end up with a pH of 3.5. So remember that we've got the Henderson-Hasselbalch equation. Okay, so we need to find out this, right? We want to know what that ratio is going to be. So we got 3.5 is equal to 3.14 plus the log of x. All right, so basically that ends up giving us 0.36 equals the log of x. And then remember, to get rid of the log, you raise everything. So 10 to the... Okay, I will come deal with you and your brother in a second. Sorry for the interlude. That would be the little one, mad because him and his brother are fighting. All right, so to get rid of the log, you raise both sides 10 to that. Okay, so 10 to the 0.36 gives me a 2.3 ratio. So I need the ratio between the two to be 2.3. Okay, so in this example, student must create a buffer with a pH of 6.2 from this acid, which has a pKa of 6.5. So what do we need to do to adjust the pH down to 6.2? Hopefully you said that we need more of the acid than the conjugate base. Okay, so we need for the that would be this one, right? Okay, so I need for my acid to be greater than my concentration of the conjugate base, and that will lower my pH from where the pKa is. All right, now also when you're making a buffer, don't forget buffer capacity, okay? So if you know the maximum amount of acid or base that the buffer is going to be exposed to, that can help you to determine what concentrations you need for your conjugate pairs so that you still have the pH range that you need. All right, so here is an example. So if we want a buffer, a 0.5 liter buffer where HA and A minus have similar concentrations, okay, we want to estimate the concentrations of the weak acid and the conjugate base in order to get a pH of 4.8 and prevent a significant pH change when 0.125 moles of NaOH or strong base is added to the system. All right, so first step is to pick our pair. So we need to know our pKa's of our two potential weak acids. So we've got a pKa of 3.18 and 4.74. Okay, so if we need for our pH to be 4.8, we're definitely going to go with the acetic here. So we're going to have a this, and then of course its conjugate base, which is that. So this is the pair that we're going to use. All right, now let's get on to trying to figure out what we need our ratio to be to achieve that pH. And then after we determine what we need our ratio to be, we can determine what how much we need concentration rise of our weak acid and base to counteract that strong base. All right, so I need my pH to be 4.8. My pKa is 4.74. So basically my log of my ratio is equal to 0.06. So my ratio is 10 to the 0.06, okay? So if I solve 10 raised to the 0.06, I need my ratio to be 1.5. Okay, now, the next thing I know is that I need a 0.5 liter solution, and I need to counteract this many moles, okay? All right, so if I had 0.125 moles in a 0.5 liter, that would give me a concentration of 0.25 molar. Okay, now we need to think about what do we really care about here. So we care about counteracting that strong base. What's going to counteract that strong base is our weak acid. So we need our weak acid concentration to be at least 0.25. So our ratio is 1.15. There is going to be our concentration of our conjugate base, and we need our acid to be 0.25. So if I cross multiply, I need for my concentration of my conjugate base to be 2.875 molar. Okay, so I need that to be the concentration of my conjugate base, and I need at least that to be the concentration of my acid. All right, and last but not least, let's touch on a practical application of buffers. So let's talk about buffers in our body. So the most important buffer in our body is the bicarbonate carbonic acid buffer. It regulates the pH of our blood so that the pH of our blood stays close to 7.4. The lungs help regulate that pH by removing carbon dioxide, which essentially is carbonic acid. For the purposes of this activity, we're just going to focus on the buffer in the blood and not worry about the lungs and all that good stuff. All right, so our Ka1 for our carbonic acid is right here. So step 1, the pKa of carbonic acid is 6.35. Oops, 6.35. Okay, so if we're comparing the pKa of carbonic acid to the pH of our blood, what can we say about that ratio? All right, so what we know is that our pH of our blood is 7.4, whereas our pKa of carbonic is 6.35. So we definitely have way more of the conjugate base than we do of our acid. Okay, so what that basically tells us is that our ratio is going to be greater than 1, okay? Because the top has got to be a bigger number than the bottom because our pH is higher than our pKa. All right, so do we have more bicarbonate ion or carbonic acid? Well, we already kind of answered that one in the previous question, right? We definitely have more of the conjugate base, which is the bicarbonate ion. Okay, so based on that, is our body producing more H pluses or OH minuses? So if our body naturally is has the buffer system with a high concentration of the bicarbonate in it, the bicarbonate is going to react with H pluses, and it is going to, in turn, make more of that carbonic acid. So we definitely have a high concentration of H pluses in our body. And I already answered E because I already wrote the equation. All right, now, if we were to draw a particulate diagram of the carbonic acid buffer, we need to draw 3 carbonic acid molecules and then an appropriate amount of bicarbonate ions. Okay, so first off, this is what my carbonic acid looks like. So it's like a box with the little colored in circle on it. So it definitely says that I have 3 of those, correct? So Definitely got 3 of those suckers. So 1, 2, and 3. All right, now we know that this carbonic acid is a weak acid, so it's going to be in equilibrium, meaning that there is going to be some dissociated H pluses and HCO3 minuses, okay? So that right there is me only drawing the carbonic acid molecules in equilibrium, okay? So that's all I've got so far. All right, now I know based on what we were doing earlier that I should have more of the bicarbonate or the conjugate base than I should of the my carbonic acid, my weak acid. So right now I have 1, 2, 3 of my carbonic acids. So I've got to have at least 4 of my my conjugate bases. So 1, 2, 3, and 4. All right, now, and understand that this bicarbonate ion, there's also spectator ions in there that are part of that salt, right? Like perhaps sodium or potassium. I'm not going to draw them, but just understand there are like some sort of spectator ions down here, okay? Something like that. All right, now the middle box wants us to draw the same buffer but with some added acid. So we want to draw the products after 2 hydrogen ions or strong acids are added to the buffer. So we know if we put H pluses in there, all they're going to do is react with our HCO3 minuses. So I'm going to go ahead and draw my original carbonic. So I'm just going to basically make an exact replica of what I have right now, and then we can go back and add our H pluses in and analyze how that would change our buffer situation. All right, so okie dokie. So at this point, I have recreated the buffer system. You see we have 1, 2, 3 of our bound acids. We have the 1 dissociated acid, and then we have 4 of the bicarbonate ions. If 2 hydrogen ions from a strong acid came in, they would basically just bind to 2 of the bicarbonate ions. Okay, so now you'll have 1, 2, 3 bicarbonates to 1, 2, 3, 4, 5 carbonic acids.